a software engineer working on Google App Engine, and that's what I'd like to talk about today. As you heard in the keynote, App Engine is a way to run your web applications on Google software and inside Google data centers, taking advantage of our scalable hardware and scalable infrastructure. The goal of this product is to make the cloud more accessible, to improve the internet by allowing richer applications, and by allowing anybody to write a great application and get it online and get it to start serving requests. This is the infamous box slide that Chris referred to in the keynote. He doesn't like this one too much. What I'd like to talk about is why we decided to build this product. So our team, based on our experience both outside of Google and inside of Google, we realized there are a lot of problems, headaches, and frustrations that go into actually getting an application onto the internet. So you have a great idea. The first thing you do is you write some code. That's that small PHP box up on the top right there. Now, before you can actually get this thing really working and start getting users towards it, you have to do all the maintenance and setup just to get that PHP code to run in a nice environment. You're going to need a database, MySQL, you're going to need web server, Apache, you're going to need operating system Linux. This is assuming you're using the so-called LAMP stack, LAMP stack. Well, you got to configure your tables, get your schema set up, get the right libraries installed for Apache, get all your extensions set up correctly, get the right operating system version set up. And then, of course, that's all just software. You need some machines to run that on. So you got to buy some virtual or some real machines out there, and that takes some money. So you've been working a lot on all this stuff, and you can actually now get like a few users. You can demo it out. But then once you start getting any more users, you have to think a lot harder about your database. Well, maybe you need to shard your database. Maybe you need your front end running separately from your database servers. Maybe you need a NetScaler or some kind of load balancer on top of your Apache. Maybe you need a lot of things. You kind of get pushed. As more users come in, you're in like a reactive cycle where you're constantly trying to make your site just good enough, just barely trying to keep ahead. And you can look at examples such as MySpace infrastructure. They put out a really nice design doc talking about the history of their software over the last 5 years and the number of complete re-architects, refactors they've had to do. It's a lot of work to get all these things working correctly. And on top of that, you've got the kind of constant nag of things kind of break. Maybe you have some monitoring set up to let you know when things go wrong or something, but you still have to do something. You've got to log onto the machine and make sure that the server logs haven't overflowed your hard drive. You got to use the latest security patch, because you don't want your site getting hacked. You don't want to lose your precious data or expose anything that's private to people. It's a lot of ongoing work. And so, it's a lot of ongoing work. But you spend more time just maintaining your code than you do writing your code. And we think this is really bad for application developers. And that's why we have Google App Engine. Google has spent a lot of time thinking about all these problems. We built a lot of products over a history of 10 years. Google Maps, Google Web Search, ads, news, all kinds of stuff. And along the way, we developed a large number of software infrastructure, and we developed some data centers. And we're trying to open up use to these to anybody. Specifically, we spent a lot of time thinking about, getting some feedback there, large-scale storage, indexing, analysis, and serving data. And we built some really good infrastructure for each of these. I don't know what the feedback comes from. So, for example, you have a product like Google Maps. This has got to store a lot of data. This is for the map tiles, for the businesses listings, for the geolocation information. It has to construct some pretty interesting indexes over all this data. It has to serve it all up to billions of users every single day. We have something like machine translation, where we're doing automatic machine translation between 20 different languages. For this, we had put together some really powerful analysis tools and data processing infrastructure. And of course, Google search is pretty famous as well. And for that, we put together some extremely efficient and high-scale indexes, and combine that with a really great ranking system. And this is today's pretty much de facto search engine. So the other point is that Google is also constantly investing in our hardware. So millions of dollars constantly going into building up new data centers, optimizing these data centers. We have some of the best networking infrastructure in the world. We have some of the best custom hardware designs for our machines. We're getting a lot of memory, a lot of disks available, a lot of CPUs to run all these products that I've been talking about already. So we're trying to combine this good software and this good hardware. These are the major design goals for the product. We want it to be easy to use. So we want to reduce the time it takes from when you have that first great idea to when it's actually running on the internet. We want to make it easy to use APIs that give you the features that you need in writing applications. And that the most direct way to use these things also will scale very nicely. And that's the easy to scale thing. So some of these technologies I'm talking about, like Bigtable, or our Gmail message routing system, or our URL fetching system, these are all things that existing Google products use. And these are the exact same stuff that we're offering up to you guys. But we think we've also designed APIs in a way that the most natural way to use them is also going to scale nicely. So when you go from 1 user to 1,000 users to 1 million users, you don't really have to think a lot about your application. We'll just kind of run it on more instances, give it some more machines, and that's all it's going to do. And so that's a constant theme for us, is horizontal scaling. We get more users, but we add more machines, and nothing changes. The latency stays the same. The overall functionality of the site stays the same. Third goal, which is very important to us, is that it should be free to get started. So all developers are given a free mounting quota, which gives you about 5 million page views a month, depending on how you actually use it. In the future, you'll be able to purchase additional quota, but there will always be a free mounting quota that anyone can get use of. So the reason that we really care about this is that we think the upfront costs can be a big problem for entrepreneurial developments. We really want to enable people to play with the system, try it out locally, but also play with it in production. Really quickly iterate, and we don't want to make people wait to give us money or get the right credit card transaction set up. As developers, within our team as developers, we find that having to pay anything is a huge barrier to entry. So this is going to be a consistently important goal for us. So yeah, free to get started, you can try it out, 5 million page views a month. And then once you start getting additional load, right now you can just kind of ask for more quota, and then going forward, within the next 2 quarters or so, you'll be able to pay for additional quota. But even so, you're going to pay for what you actually use. In our system, you don't have to pay for entire machines. You don't have to rent for your peak capacity. You just pay for the raw resource usage that you actually manage to. So you pay for your CPU usage, your bandwidth, things like this. You don't have to pay for a cluster or a machine or the power or something like that. So it would give you meaningful units of resources. All right, so let's talk about the major components of that engine. And then later on, I'll go through some demos of some actual working stuff. So the first is our scalable serving architecture. We built the entire thing out of tape and what appears to be some really fantastic switches here going on. So yeah, there's something to do with just constantly switching every single network request that's coming in. Yeah, that's it. So When you deploy an app on Google App Engine, your code is automatically pushed to a number of fault-tolerant servers. As usage of your app increases or decreases, we're going to detect this and then automatically deploy your application on more servers. So you don't even have to do anything manual at all. It's completely automatic in response to incoming requests. With something like a slash dot effect, where some really popular website decides to link to your website, something that Chris mentioned in the keynotes, what you notice is that it's not an immediate surge of traffic. Instead, it is kind of a sharp ramp of traffic. And what we can do is we're kind of constantly watching your application's usage. And if we detect this sharp ramp, we can deploy your application to enough machines in time so that you handle the peak of the ramp and handle full slash dot. Of course, after that, your application will have organic growth, which is much easier for us to adjust to. Here's a simple architecture diagram. So we have incoming requests, and these are coming from a number of browsers or from client applications. So this was a surprise to me that I initially thought that Google App Engine would be primarily used as a browser system or a browser application system. But it turns out that there are a lot of ways in which you can make use of it otherwise. So you can have a pure client application running on an iPhone that makes HTTP requests out to a Google App Engine application, which then serves up the data that's served on the iPhone. And there's a number of people that do this. It can also be the backend for like an open social container or any other kind of client application. Something that works within an existing container or an existing system, as opposed to like the kind of pure browser application where I'm more familiar with, like Orchid.com or Google.com, something like that. But yeah, incoming request comes from somewhere, speaks pure HTTP to one of our front ends. Our front ends are located all over the world, and then, within a significant number of continents in the world. And then the front end knows which app server is the one to talk to. So it's going to send that request across a Google network link to that app server. And then each app server is going to be responsible for some number of applications. And then this load balancer system here is constantly watching all the app servers and then moving around which applications are served on which app servers, when they need to grow, when they need to shrink, when we just need to move things around to do some defragmentation or something like that. And then within the app server, it's running a number of runtime processes. So in this case, let's say we've got about 40 or so different runtime processes. Each of them is running at the same time. And each of these is going to be processing one request at a time. And that's an important part of our system, is that it's very request-based. Your code runs, but it gets a request through the CGI protocol. So it gets some environment variables and a standard input. And then it's going to run, and then it's going to write the output and then stop. So your code is running when it's processing a request, and otherwise it's not running at all. And even when it's processing a request, it's not usually doing pure CPU burn. It's usually doing a mix of making API calls and doing some local computation. Local computation such as, making requests, receiving responses, and translating responses, filling out templates. But these API calls is like a very significant part of the system. So you can make a call out from an app through the API layer out to Bigtable or the data store, out to Memcache, out to image manipulation system, out to URL fetch, something like that. So the app will spend about 20% of its time actually doing some computation and 80% of the time waiting for an API call to respond. So we can run all these processes on top of each other on one machine and let the kernel figure out how to schedule them correctly. But it's also nice that we can deal with cold applications very well. So what's a cold application? Let's say you have a very small application put together. This is a toy for you and a couple other people. And it gets like a couple of requests a day or a week. Now, without App Engine, if you wanted to run this, you would need to do something like, buy like a virtual hosting system or something. Maybe the cheapest you could get something like $10 a month. But even $10 a month is a lot for something that does like 5 requests a week. For us, we can do this very efficiently. So typically, this application won't be loaded anywhere. There will be no runtime processes right for this application. Instead, a request will come in, and the app server will see, oh, I don't have this application loaded. So it's going to fork off a new process, load the application code, start the interpreter, and then send the request. And so we can go from typically having no memory consumption whatsoever for this application to starting a clone, initializing it, and actually sending a request. And it's just like a 50 millisecond cost for us. So we can actually do a really good job here of having a large number of cold applications that we can easily serve, basically from this on demand. And then we can, evict that process from our app cache here when we're done with it, and reserve runtime processes for the applications which are consistently serving lots of traffic. So yeah, it's an important part here that it's request-based. Your code just receives requests and emits responses, but it's up to us to schedule which apps are running which app servers, and even within an app server, how many processes are running for that application. When to create a clone process, when to kill one, when to grow an app, when to not grow an app. And it's really nice because at this level, we can make some really intelligent decisions, but we can get some really good utilization of these machines. With a few number of machines, we can actually serve an extremely high number of applications, which is great because it means that we're enabling many developers to get their code running on the internet, and we just want to run it all for it. Second major component is the data store. And data store is built on a storage system that was developed at Google called Bigtable. You can actually read more about Bigtable by looking at some research papers that have been written by some Google engineers. But the key thing about Bigtable, and for this discussion, is that it's not SQL. Instead, it is, but as opposed to SQL, it's going to allow for some really rapid and flexible developments, as well as a storage system that will automatically scale to your needs. So it's based on Bigtable, and the fundamental concept in Bigtable is a table. And a table consists of a large number of rows, and it's sorted. So it's like a large sorted array. And for every row, there's a row name and a row value. So this large array is sorted by the row name, and then it's not sorted by the row value. And what Bigtable is going to do is going to break up this large array into what it calls tablets. So some consecutive set of rows is a tablet. And then it will automatically change where the tablets are based on usage. Maybe this tablet starts getting a lot of data, so it decides to split that tablet in half, the two tablets. Maybe this tablet is getting a lot of requests per second. It's really heavily accessed, so it also will decide to split it up. And then each tablet will be served on potentially a different tablet server. So this is really nice. You just keep adding data into this table, and Bigtable is going to automatically figure out how to split onto more machines. Or maybe you access some things more than others, and it'll figure it out. So you don't have to do manual shard configuration, and you don't have to think too hard about it. It's automatic, and it can make decisions that you may never have even considered making. Like it might make this very small set of rows have its own tablet because it's accessed so frequently, but everything else is maybe just on one big tablet. It doesn't care because it's not too large and it's not accessed very frequently. So it'll automatically manage this data and save you a lot of grief. So yeah, that's the key thing about Bigtable is that it was designed from the beginning by Google to solve the problems that we were seeking in our products. And it's designed to be distributed across multiple servers and multiple disks. So something like each Bigtable instance can handle something like thousands of machines and tens of thousands of disks. But because, this picture here is one of the original Google data centers. You might see that in some other talks as well. So because the data store is not a relational database, it means that it doesn't support some functionality that you might expect, such as joins. The reason is that we found joins are very difficult to implement efficiently in a distributed storage system with thousands of machines where data is perhaps located all over the place. Whereas, alternatively, Bigtable is designed in the beginning to work across this many machines and many disks. So, while you may not be able to use joins, what you gain is a data store that can scale efficiently to millions of users. And we are confident that if you try it out, you might actually like it. You end up with an object store instead of a relational store. And so it's like imagining, what if I had like one process with one large address space, just like an infinite address space, and there are objects inside this address space. How would I use that efficiently to write an application? So it's not too different from how you would code something like just a regular program running on C++ or Java or whatever on your local machine. And keep in mind that we do support a number of important features. We do support queries, and transactions, and deposit indexes as well. This is like an example model class. So we see that this is a model of an entity. So an entity is the fundamental storage unit inside of the data store or inside the application. An entity is just an arbitrary map of key value pairs. And there's no real schema, so you could change your code and add in a new property anytime you'd like to, and we don't care. In this case, we've got 3 properties, and the values have different types. So we have 2 string properties and 1 datetime property. You can also do integers, lists, floats, different kinds of properties that we built into the system. And we'll generate indexes on each of these properties using the comparison operator that's the natural one to use for that type. In this case, you can see some interesting features. Like at the bottom you can see that we have auto now add equals true. So what this is going to do is that since DB model is just a Python class, we can extend it however we'd like to. We can just inherit and make modifications. So in this case, when you construct a shadow entity, it's going to automatically fill the when property just using the current time. So you don't have to do that inside your code. Further, you can subclass the shout entity, and you can fill in other properties automatically based on other things. You could have a factory which constructs a shout property if you'd like to, or you can use class inheritance to kind of have more full control, something that you may not have had otherwise in other systems. Here's an example query over the data store. So while we do not use an SQL database, we happen to create something called GQL, which stands for Google Query Language, which is a limited subset of SQL to try to make it easier for SQL developers to query over the data store. In this query, we're fetching 100 shout entities, but we're matching by the Brett, or by the cool property. So we're trying to get shouts made by Brett, and we're ordering by the time they were made. The third major component is the Python runtime and libraries. Python is the first language that application supports. You write your server-side code in Python, and then you can serve static files such as HTML, JavaScript, XML, whether you like Flash. And that will run on the client side. We use the HTTP and WSGI protocols, so you're welcome to use whatever web framework you would like within Python. So we include a full Python runtime, supporting roughly 95% of the standard libraries. These are all libraries that we've audited in some way to ensure that they're not going to do anything malicious on our machines. Because at the end of the day, your code is running inside of one of our app servers on the same machine, maybe as a GFS chunk server or a Bigtable tablet server. you're running sidecar data centers on the same machines that run our other products. So we're pretty concerned about security here. So we cut out 5% from Python runtime. We've also cut out a number of other things, such as opening a file for write, opening up a socket, or a large assortment of system calls that you may try to make. It's important to note that Python is the first language supported by Aperture. There are more to come, and we're actively working on supporting additional languages. And we welcome your input as far as which ones we should start tackling next. Fourth, there's the software development kit. And so this is pretty cool. This is a launcher program, but we also have a completely pure Python SDK program that runs on Windows, Mac, and Linux. That is a complete implementation of all of our APIs that runs entirely locally. So you can do purely local development, have APIs that work the same way. You don't even need an internet connection, and you can get some really fast, edit and compile test cycles. You can make a small change to your code or to your templates or anything. Then go to your browser, hit refresh. The change will take effect immediately. Finally, there's our admin console. So once you deploy your app to Google servers and it's running live, this gives you a window into how it's doing. We have some nice graphs here which show you, the request per second or CPU consumption per second graphed over a 24-hour period. You can see quota usage. You can see some information on how each of your handlers is doing. So on a per path basis, what's the efficiency of your application? You can dig through your logs. We have some really powerful search tool on your logs. So let's do some kind of example. And I'm going to try to stand far enough away from that speaker so I don't have too much feedback, but it's going to be a challenge. That's what we got. So, that was there. Just press the keep going button. Okay. So here's an example application. This is just a configuration file. So the application name, I'm calling it shoutout is real. This is an application where you just do shoutouts. I don't know if that word means anything to you, but some person will make a message. It's kind of like a public message board. So we can control different versions here. You can run multiple versions of the application at the same time, and you can request them individually if you'd like to. So this is version 1, running in Python. And then there's a handler at the bottom. And this is a fairly useful tool that is a sorted list of handlers. The first one that matches based on the URL's regular expression, that's the one that we're going to send it to. So you can use this to really quickly and efficiently card out which request should go to which source files. Yes, those two. Okay. So this is some Python code. At the top we see some imports. Standard Python style here of having some common libraries, OS, datetime, WSGIRF, and some app engine specific libraries, web app, and template, and DB. We installed this web app template within App Engine, which is a fairly simple web framework to use in Python. It's backed by the Django libraries and by a model class that we defined itself that gives similar look and feel to Django, but is implemented fairly differently. You can use this or you can scrap it and use anything else you like to. We're based on HTTP and WSGI, so use it however you'd like to. The important thing is this shop entity. And again, this is the same one from the slide. So this defines the property types and values that are going to be used for all shop entities generated by this program. At the bottom, this is another handler app running inside of the code. So for all requests that are sent to main.py, it's going to use this map. So if the URL is slash, it's going to send it to that handler object. And if it's slash shout, it's going to send it to the other handler object. In this case, they're the same, but you could have many different kinds here. But yeah, this is just fairly common initialization code. Okay, so here's what the handler actually looks like. So on a GET request, so you can see here we have a handle object and we have a method for each HTTP method. This can also support, head, delete, but in this case we're just using get post. So for get, we will query the data store and get back 10 shout entities. That's what you see happening there. And then we're stuffing them into the templates. And then we're rendering our templates. So this was fetch from the data store, construct a dictionary, then render the template based on the dictionary. And then on post, we're going to construct a shout entity, and then save it to the data store, and then rewrite the user backslash. So, what is main.html? It's this. So at the top, it's a very simple web form. Just a regular post form with from a message. Got it. And then after that, we're going to have print out up to 10 shoutouts. And so this is using the Django template library. We can do constructs such as conditionals, so in this case we're doing a loop. So for every shout in the shouts list, we're going to print who it came from, who to, at when. So let's try without when first. Then I can go here and that's running. So first, let me fix this. I don't know why that's up. Okay, that's better. So this is the application running on my machine now. Just localhost 805. And so I can say, I can see doing that. Right. So let's go back to that application. So here, I can add that back. Shout.when. And there we go, we get those timestamps popping out. I can also do other stuff, but no, we don't have a title here, so it's not a title. Oh, okay, title. Cool. And how about changes to the code? So I go here to the code, instead of 10, or, let's do this, so basically, so, other John. Okay, so let's go and reverse the presentation here. So here, I can make that ACD for instead, and we flip the results based on who it came from. Go back. So this is that really fast edit, compile, test cycle. There's no compile either, it's just edit, test, it's really here. And this works for all of our APIs and on top of the data store. So that's great. Now we can take that exact same code and deploy it. Okay. And here it is running. Now this is on the internet. You guys can add your own shoutouts as you'd like to. Although I don't think it's actually up to date yet. Yeah, the password, right? Might have been stuck on the internet connection there. So that's looking. Yeah, that's fine. Oh, that's really weird. Let's try doing it directly from the terminal instead. cfg.py. It's a pure Python code that we'll use. I really have no idea why the SDK did that. I haven't seen it before. Extremely embarrassing, but let's move on. Now this is the real one. You guys are actually writing to it. Fantastic. Hope you guys aren't writing anything too dirty. But we got the title up there as well. EDP is real. And oh my god, I melted from Bill. Oh my god, it actually works on the time we're on. Cool. Alright, let me show you some other applications which are a bit more interesting than this one. Something we recently launched called Google Moderator. We use this a lot inside the company. Whenever we have a tech talk or a visiting speaker, that we'll set up a moderator room. Because what a moderator does is, let's see, ask the world leader. Barack Obama. So you kind of add questions here, and people can vote on the questions. And so it's a really useful way to kind of have the best questions right at the top. So if Barack Obama came to Google or something, we would use this system. And that way, maybe 1,000 people watching the talk, they would all just, post questions here. He would just answer them from top to bottom. At Google, we optimize everything, and so we can optimize our tech talks. And this is what we use. And we've opened it up that anyone can use this now. You can make your own room and use this for anything you'd like to. And it runs an app. So, cool. Here's another one. This is Buddy Poke. This is a bit less serious. This is a video poking software application somehow. I don't understand it really. I'm too old. It runs in a number of open social containers, so you see Orchid, you see HiFi, you see Netlog. It's a fairly popular application. It's currently our biggest application, getting somewhere in the order of 500 QPS. But yeah, we expect more big applications to come. So it's cool. We got something out here that someone had this idea. They were able to do entirely outside of us. In this case, they asked for additional quota, we gave it to them, and their application is doing fine. They got millions of users, and I think they're actually one of the largest open social apps out there at all right now. So, yeah, it's great. They're able to quickly develop, they're able to just focus on the user, focus on the applications, which is what they're really good at. I'm really good at infrastructure. I would not have come up with this. They came up with this though, and they were able to optimize it and continue to improve it. And to give it to more locales and more countries. Whereas I decided to focus on, the app server or the data store. It's a really great separation of duties.
Is there time for questions later on?
There will be time for questions,
okay.
Yes. So, here's another one. We have, this uses our URL fetch API. It pulls a lot of data from the Twitter feed, and it's aggregating that. So this is currently what's hot on Twitter. People are tweeting about John McCain and Texas Tech and Halloween and daylight savings. So I guess daylight savings switch is coming up for the U.S. or something. I don't know what's happening for Israel. Oops. There's another one. This is another one of those internal tools that we did opened up using App Engine. So this is Refill. It's a code review tool. We have something like this that we use inside of Google. It's a really useful UI for doing code reviews. So if you send out like a diff, these are all the lines I like to change these source files. And it'll show up here. I'll show you what that looks like. Here it is, fast. So people can comment on individual lines. They can say what they like, what they don't like. Source. So we see here that this change is, modifying some comments mostly here, adding 2 new macros, one for Solaris, one for ZOS, going on. So we use something like this ourselves because Twitter is a really big deal for us. And so I can just come here. Oh, I got to log in first. Well, let's log in. So I'm using the users API here, and you can see that I'm going to log in through Google. Great. Once I've done that, I can come through here and say, what's yours? Great. And then I can use the email API and send my comments out to the person who's proposing this review. Cool. So these a lot of different APIs there. Here's a really simple one as well. This is my text file. It's just a text editor. It uses the data store back. Yep. Nice revision history. And, yeah. You have something like this as well for adding people, but here's another one built on top of that. Just another really simple tool that you might want to come up with. Maybe you don't want to spend, $10 a month to host this guy. You just want to get it on the internet, and we'll take care of it after that. There's another one. There's another Google product that we use. Google Code Jam 2008 ran on App Engine. This is a programming contest. And so we had the recent EMEA onsites. So programming contest, you can see problems, inputs, and outputs. So that's kind of a Gmail style theme as far as UI goes. It's got some questions and answering, and we've got scoreboard feature. So I don't see any Israeli users on here. So those of you guys got crushed by the English and by the Russians, but I don't like my style. So yeah, what's next? Here's the app console. Yeah. I think it was based on Git, yeah. Yeah, that's something you definitely do write, your front-end code in Git using Java, goes down JavaScript and then posts that on App Engine, but then use Python as your backend, using like Ajax or JSON or something to communicate between front-end code and backend code, definitely. So yeah, these are admin console, you see request segments, getting code usage, you see information on individual URLs, and then we can also dig down to the logs. So I got this section here. So I can see here's the log information that I wrote out. And finally, here's like the exception that occurred. So we really see a lot here. But then you can also do searching on this. So maybe I want to search on my logs. What else happened with this Kaiser application? So okay, here's all the other requests that happen with Kaiser. Fantastic. We have these kind of tools ourselves internally at Google, and so we're trying to provide this also out to other developers. Quick rundown of the APIs. We've got the data store API I mentioned, the big table storage system. We have an image manipulation API. We've got mail, and memcache, URL fetch. And again, these are all based on existing Google products. So the image API uses like some of the same libraries that Picasso uses. Mail API based on Gmail. Memcache API based on, actually that one's based on the open source Memcache implementation. But then URL fetch based on Google Accelerator, uses API based on Google accounts. And we're going to keep adding APIs and keep adding languages. And one important thing is we recently launched this product roadmap saying what's going to happen next. This is the short list of things we've committed to before March 2009. And so storing and serving very large files, something on the order of a gigabyte or so, being able to upload videos and serve videos, that kind of thing. We want to have really great data store import and export utilities so that you can start transferring many gigabytes, hundreds of gigabytes into your application, getting it out. Maybe you want to do backup, maybe you just want to do some local analysis of your data. You're going to have billings so that you can start paying for more resource usage as opposed to just asking for it. And then a new runtime language. At this time, I can't announce what that runtime language is, but there's a new one coming before March. And also an uptime monitoring site, which is also a fairly novel idea for Google. We're going to have a site which has really in-depth analysis of how our APIs are doing, what the latencies are, what the error rates look like across the board. And that way, if you see reports of errors on your application, you can reference that back to how the overall system is doing. Yeah, so let me know what's going on. Yeah, we've got about 10 minutes or so for questions and answers. So let's jump into that. You can just be very loud, or you can use this microphone here in the middle of the room. All right, you guys turned up.
Yes, is it possible to use the App Engine in order to run and deploy Java EE application?
Is it possible to run App Engine to run a Java application?
Yes.
So right now, Python is the only language that we support, and we'll have another language coming before March.
Is it in the roadmap or
something? Oh yes, this is the roadmap right here.
No, but would it be in the roadmap using Java EE.
Java EE? What is Java EE?
J2EE.
J2EE.
Enterprise.
Right.
One of the most common.
Right. I can't really answer that question because that question predicates that we're launching Java. But this is what I can say. I can say that we're supporting a new runtime language. Thank you. Yes? Mm-hmm. Yeah. We are working towards a cron system, but you can also use there are various web cron systems. You can just run a cron tab on your local machine. There are some people, some websites that will just do that for you, where they just kind of you specify when you want something to occur, and it's going to just make a URL call. So it's just going to, on some schedule, make a URL call that will go into Google App Engine. And we're working towards making that better. It's just not on the short list of releases here. Yeah. Sure. Let's see. This is a useful question. This is not. Show you some numbers here. This is the current free quota. If you want to use more than this right now, you just ask us. But eventually, if you use more than this, there'll be a way to pay for additional usage. I think those use storage here at all. Let's see, it's higher up. It's like 500 megabytes storage per application by default for free. And then after that, this is like the number of maybe API calls or bandwidth consumption we can do in a day. Right. Okay. No. I have a much better slide. Sorry about that. So you do something like this. So instead of that GQL query, you would wrap it in these 3 lines of code. So you would get, so you just get the results out of memcache. If they're not there, then you do the actual query execution, and then you'll add them back. And then on subsequent calls to memcache, it's just going to get, that first time will be true, it'll be back the actual data. And in this example, we're setting an expiration time of 60 seconds. So the cache value is going to be out of sync with the real true value, but memcache actually has a number of other things as a setter, an invalidator, it has support for counters, so you can keep the cache value in sync with the true value. So it's a pretty cool implementation here. Yeah. Right, so the question was about deeper integration into all the other APIs here. Right now we don't use memcache. There is some level of caching that occurs within Bigtable natively, but it doesn't directly use memcache for that kind of stuff. But you can pretty much use memcache on top of any of the APIs you'd like to. You could wrap like a URL fetch call with memcache if you want to. Maybe you can wrap your template rendering on top of memcache. It's very generic, extensible API. Yes? Right. That's certainly an interesting question of can we make it so that you don't even have to think about caching whatsoever? But it's a bit difficult just because with people's concerns about cache consistency with the true values, how long to expiration times, how to invalidate or keep the cache value in sync. It varies a lot on a per application basis. And so, if we do some caching across the board, we want it to be, maybe very simple caching where we know that we don't have to make any trade-offs, but a lot of the times applications do need to make trade-offs, and it's up to them to decide what's the right, trade-off between, the consistency of the cache value and expiration time versus the number of API calls they're willing to make. I'll take you second row.
I have a question not about the technical side, but about the administrative side. So
Okay.
I'm understanding Google is going into the web hosting business. For example, right now we have a web hosting company that is getting excellent customer service 24/7, and I can call them, the human answer will be available to me within like 1 minute, and probably with a very good answer. They also can use it legally. Like, is Google ready for this kind of job, being a web hosting company?
The question is, how is Google going to be able to handle the customer service side, or the ability for developers to get in-depth technical answers as far as quota usage or yes, question. So the person's comments is that he doesn't believe that Google can answer the question within 5 seconds, and it is a very difficult challenge, especially the more detailed it gets here. It's not a very simple consumer product. It's not just like help me add a task to a calendar. It's my data store latency is 200 milliseconds. Why is it? And there can be a number of reasons, and it's a fairly hard thing, and it's a very hard challenge for us. Sure. Take another question. Yes. Tighter integration with GWT. Yeah, so I mentioned already the existing integration, which is that you can use GWT to write your front-end code in Java, compile a JavaScript, post that, but then use make backend calls into Python. You said what type of integration would you be interested in? So I'm not entirely sure what you're referring to, but maybe after the session we can talk more in depth about how to make that easier for you. Yeah. Well, so can I elaborate on the difference between SQL and GQL? GQL is a subset of SQL. It's a fairly limited subset. It's a read-only language. It's only interested in simple gets and simple queries. And the internet will be fast enough. I can show you the full reference for GQL, but you can just kind of go to the code select here. What else is this thing? So I can show you. This is it really. Just where, order by, limits and offsets, ancestor queries, simple comparison operators. It's not extremely extensible. It's really designed with data store mind of being able to do queries and gets on individual property names or combinations of properties. I'll move on to you had. Things like that. So I kind of glossed over it, but we do have the Zeus API, which is backed by Google accounts entirely. So people can log into the same account that they're using to sign into Gmail. So we deal with all the problems there of security, working across different browsers, using an authentication system which is secure, which we're comfortable with ourselves, sort of Gmail. But also you don't have to deal with like lost passwords, people asking questions about its system, FAQs. So we have that. We also recently launched that we're going to be an OpenID provider for Google accounts. So that's another thing you can use to make use of OpenID for logging on your application. And that's independent of App Engine really. That's any website can start using that right now. And then I think also, if I can find this, we recently launched something called Google Apps Labs. That's regular Google Labs. More like it. So we're running a number of So Google Moderator, that's one of the things I showed you earlier. The code review tool, these are a number of tools that we're going to start opening up to anyone who has Google Apps already installed. And we're going to continue to do more and more like that. So it's kind of like Google Labs, but for Google Apps. We can continue to get these applications out there, ultimately running on App Engine, but then get them integrated to Google Apps so that people can start using this for whatever they want to for their company or organizations. And then I guess the broader question was, can people contribute to that other than Google? And I don't really know the answer to that. That's a good question. Yes. Is MapReduce available? The more general question here is offline processing available? So I mentioned at the beginning that right now it's completely request-based, that your code is handling one request at a time. But we are actively investigating additional computational models so that you can have maybe code that's running offline, not in response to the user requests, that can start doing some serious computation, processing large amount of data, still maybe using the data store, maybe using something else, but being able to do like offline processing. And you can read a lot more detail about the different proposals for that on Google Code. We have an issue tracker there where the people we've been discussing the different ways in which we'll provide offline processing. It's like a large community discussion on this right now. Okay. So can I create an application that runs within one enterprise domain running on Google App Engine? And actually, yes, this is something that works right now, where you can bind an application to a specific domain, and it will only allow people to log in from that domain. And so if you do that, then that's it, and it's running on Google App Engine. We also support serving off of any hosting you'd like to. So a lot of these examples kind of go all over the place. So this is codereview.appspot.com. So we have all of appspot.com for you to use. But then you can make your own hosting here, like www.current.fm or buddypost.com or something. And these will all serve off of App Engine. So you can use your own hostings. You can restrict hosts to serve within one dasher or one, whatever Google Apps for your domain you like to. Yeah. Yeah. So can we make MapReduce available? And then again, it's the same topic about offline processing that the same answer I just gave just a minute ago. So let's move on to some other questions. Okay, looks like we're running out of questions, and we've run out of time a while ago. But I'll still be floating around today to answer questions. Those are going to be Code Lab coming up at 2 o'clock or something like that. I wanted to thank you all for coming to the talk. I hope you learned something.